Developed solar thermal systems are under the advanced stage of patent grant, while he has been granted one design and two copyrights. Dr. Singh is currently working on one ISRO and one SERP-sponsored research project of a total grant of about 60 lakh. He always welcomes students across the country to join his research group to learn the CFD and apply to nature-inspired engineering problems. So today's topic for Dr. Satinder Singh is giving talk on finite volume method solutions to fluid flow problems. So thank you, Dr. Satinder Singh, to join with us, and it's over to you now.
Yeah, thank you, Dr. Manoj. So I welcome all the participants, to the lecture on FVM solution to fluid flow problems. Dr. Manoj, I'm audible.
Yes, sir, absolutely audible.
Okay. So before to start, the numerical approach, I just want to go through some applications of CFD. So I told you, introduction to real world and engineering problems. So I just want to show you the capability, as per capability of the at present, the developed mathematical solutions, numerical approaches, and the sources and their discretization, and how closely we can present, a real world and engineering problem using CFD. And a part of that, a CFD solution not only mimic, a real world situation, but also reveal the physics which is associated with the problem. So, for example, I'm showing you one evaporation problem where a droplet is resting on a leaf and continuously evaporating. So, same we can make in a CFD platform as well. But one thing is which is missing in the experimental observation, that is the change in the variables. So, for the same problem, if we solve this in a computational platform, then we can see how the velocity changing inside a droplet, how temperature is affecting inside, so that we can relate everything with the physics and clearly demonstrate the physics associated with the problem. That is the beauty of the CFD solutions. So likewise to engineering solution, like say for microchannels, where we deals with the mixing problems, or to get a same fraction repeatedly, then we design such microchannels, where I'm showing you one experimental observation. As you can see, a common or repeated volume has been extracted through this microchannel device, where one fluid is forced in this channel, another is coming perpendicular to that, which is immiscible to that, and at this junction, it is separating this fluid, this liquid, in a equal fraction repeatedly. This is a very useful, microchannel device in biomedical and chemical industries. So before to design this solve, we can solve this problem in CFD and can obtain a optimized solution for the same related to the flow and geometrical optimization. Similar to multi-phase flow problems, where again a mixing problem, where I'm showing you a droplet falling in a water pool, and same we can solve also in a CFD platform to understand the effect of the forces and mixing properly. I'm showing you another multi-phase flow problem, filling of a dam, and very interesting problem at present for solar thermal, who are working particularly in solar thermal systems, to store thermal energy. And then we are generally using PCM. So I'm presenting you one experimental observation where on the left wall a uniform heat source has been used, and a phase change material is melting inside uh, enclosure where all the walls are insulated except this left wall. So you can see the PCM is melting continuously. You can clearly observe liquid and solid friction. But the problem is, if this wall is maintained at a uniform temperature, although this melting is not going uniform along this particular direction, we can say if this is x direction, so it is arbitrarily going in x direction. Although we are applying a uniform temperature, a straight front, melting front should commence. So it is not clear from the experimental observation what is happening actually inside, what is the physics behind this this melting front. So first, using a CFD platform, we can mimic the same problem. And the beauty of the CFD solution, I told you already, we can see the change in the variables, like say velocity and temperature both can be represented, where velocity is representing the what kind of motion is occurring inside because of the density change, and where temperature is showing you the large concentration of the temperature because of this motion near to the top surface, which is commencing this melting, more melting near to the top compared to the later section, bottom section. So porous media flow, generally porous media used to increase the convection, or sometimes this is a similar common problem where we have the dams and how much water penetration can occur. So to estimate that also for civil engineering, this is another problem of interest. So for turbo machinery, for aerodynamics of the vehicles, so CFD, everywhere it is well applicable and giving us very a true solution at present as per the capability of the latest development in the CFD. So in the electronics industries, as a heat sink, what should be the path for the fluid so that we can extract known amount of heat, which is required for the operation of these electronic devices inside. For hydrodynamics, uh, so in hydrodynamics, our interest will be a geometry must present a very less drag against the flow, so we optimize them. So in the advanced stage at present, we have fish like locomotives. So where we are taking the help of the CFD platforms to understand the various species of the fish which can be taken to locomotives at present. So this is just brief about the applications, but I'm not saying that the CFD applications are only limited to these all. It has more broad coverage and application areas. So now I welcome you all to the particular topic, which is finite volume method solution to fluid flow problems, where I'm going to discuss with you the solution of Navier-Stokes equation. So this will be the content of today's lecture. So I will be telling you in the beginning uh, how to obtain the the mathematical differential form, partial differential form uh, for continuity equation, then transport x momentum y momentum equation. We will particularly stick to the 2D problem, and then we will understand their meaning of individual term or individual differential that occurs in the differential form of these equations. So first, and the prerequisite for this particular course generally will be mathematics, fluid mechanics is transfer, because in most of the fluid flow problems, generally we also encounter with the heat transport. There are some of the recommended books. So, as you know, the mode of heat transport. Similarly, we have the momentum transport. So, in fluid mechanics, in fluid flow particularly, we have two ways particularly. One is diffusion, another is convection. You can say. So, likewise in heat transfer, conduction or diffusion we represent when energy transport due to random motion. Similarly, momentum also transport. So we will remember this one. Diffusion is one of the transport phenomena that happen in the fluid flow problem. Another is a convection, where in heat transfer, in addition to energy transfer by diffusion, energy is also transferred by bulk or macroscopic motion of the fluid. We call that the bulk movement of the fluid. So similarly, momentum is also transferred in a similar way when there is a bulk movement of the fluid or macroscopic motion of the fluid. So these two are well capable or applicable to the fluid flow problems. Now the conservation of mass. This is again the recapitulation. We already know all about this conservation of mass and momentum, conservation of momentum, and just we are revising them again. So from the conservation of mass, we particularly understand, for a control volume approach, the mass which is entering from a control surface must be equal to the mass which is leaving from another control surface. So inflow outflow must be zero. So I'm mentioning you the most important thing is what is the use of this conservation of mass. Although we cannot derive any velocity, particularly from this mass balance, But if you are using any CFD solver, then in the first point you may be saying the convergence occurring for a continuity equation. So here particularly the importance of this conservation of mass in all the solution of fluid flow problem is we will make check over the velocities that will be driving from the momentum equation using any of the algorithm further. So these velocities will be coming, and then driving the mass from or mass flow rate from velocity, we will be making check for a control volume that how much the mass which is entering same is leaving or not. For that we will set one convergence criteria, and when it will be satisfied, then we will say our solution has been converged. So this is the overall role of this conservation of mass that we'll keep in the mind, and later we will try to use it also. Now, the law of conservation of momentum, as we know already, again for a control volume approach, the rate of change of momentum of a fluid inside a control volume, that is unstudied term, plus momentum rate at which fluid leaves the control volume. We'll consider it for a momentum coming from a surface and leaving from another surface. So outflow minus inflow, because momentum will be lost in overall the fluid flow process, and then that will be equal to surface forces where pressure and viscous forces will be considered, and in addition to some advanced problems or where gravitational effect is there, we additionally add these body forces like gravitational and electromagnetic forces. So writing then for a particular control volume or for a two-dimensional computational domain, it gives us this mathematical form where everyone will be aware of this, and we generally call them governing equations and 2D Navier-Stokes equations, where the first one is representing you the continuity equation, which represent you the mass balance only, the conservation of mass for a control volume, and where now we have x momentum and y momentum, where the variables I already have highlighted you for your reference. So we will have a discussion about individual term because solution for individual term will be different, and we will remember them also. The first term in x moment, if you're following my cursor, then this term we will call as unsteady, and the combination these two we will be calling that advection, and this will be called as source, originated from a pressure force, and this is the origination from a viscous force, and this will be called as a diffusion. So similarly, in y momentum, this first is called as unsteady term. These two are advection, and this one is a source term, and this is a diffusion term. So similar the differential form also occurs in energy equation. So in a generalized way, first we will call them unsteady, these two collectively called as advection, and this will be diffusion, and last will be called as source term. Dr. Manoj, I'm audible?
Yes, sir, completely audible.
Okay, fine, fine.
Uh,
So,
okay.
so again, I'm recapitulating this. This is utmost important because we have to keep these names, with these differential forms, so that when I will be discussing further solution, then we can remember that. So first will be called as unsteady, two terms collectively called as advection. Then third will be that is a pressure term, that is source term, and then second order differential with respect to the velocity in two-dimensional coordinate space will be our diffusion term. So similarly for x and y. Then types of fluid flow we generally have, in engineering or in real world situation we encounter with external internal flow, where one example I quote here, the free stream flow across a cylinder, and for internal confined flow in a channel pipe. So we need to understand the initial and boundary condition for a CFD problem. So I'm just showing you flow across a cylinder as a problem where we have to create a geometry, uh, and before to create a geometry we need to uh, perform a geometry independence test for open channel flow or for open flow. Then we have different boundary conditions, as you all will be aware of: Dirichlet boundary conditions, Newman boundary conditions, and Robin or mixed boundary conditions. So, who are new to the CFD, for their reference, I am telling you the Dirichlet boundary conditions are those boundary conditions where, in the form of a variable, we directly assign the value to the boundary, or when in the form of a gradient or a differential, we are applying a boundary condition that will be called as Newman boundary condition, where this is for insulation. We write like del T by del y equal to 0, where for a free slip we are representing del u by del y equal to 0. Okay, v velocity will be 0 here. For a no slip, we have to change this differential to u and v equal to 0. Okay, in a mixed, where we have a Dirichlet and Newman both will be involved in as a boundary condition. So at the outlet, you can represent. I can say now they are all are the Newman boundary conditions. At the inlet, they are Dirichlet boundary conditions, where we also have initial conditions. In order to initialize the system, we have to take some initial guess. Okay, as per the initial state of a system in a real situation. So accordingly, we use, or sometime they can be initialized with the zero u velocity as a zero, v velocity as a zero, or temperature by taking a reference temperature. So time matching schemes we have, or methods we have. So we have explicit method, implicit method, uh, and then we have midpoint method also, Craig-Nicholson method, which is semi-implicit method. So for most of the time in finite volume method, we go with the full explicit and full implicit method. So what happens in the explicit method? Again, recapitulation. Although this is not the I thought to cover in this particular lecture, but for revising you so that you can particularly take the field when I will be discussing the further solution of fluid flow problems. So in explicit method, what we do uh, at n level means initial level, n representing the initial level, n plus 1 representing the advanced level, at a particular extent, let's say delta t, we generally say time step. So this n plus 1 representing the next time level. This is the previous time level or initial time level. So in explicit method, we involve 5 values from the neighbor nodes and then find one value at the next time level. So likewise, for the next neighbor grid, again we have to utilize 5 grid values at the previous time level. Then we will obtain a single value at the next time level. So one by one, we will obtain the value at each of the grid by involving 5 values at the previous time step. So this method, it is very highly accurate because uh, one by one we are assigning value, obtaining value at individual grid. Where in implicit method, considering only the one value at the previous time step, we can obtain the value at the 5 levels, at 5 grids in the next time level. So we are extrapolating at a higher level in implicit method, but it will be very very fast because considering a reference of a one previous value, we are assigning obtaining value at 5 grids in the next time level. So this method will be very fast but not accurate compared to the explicit method. So these are advantage responses I mentioned here that I already highlighted during my discussion. So again, come back to the governing equations, to the Navier-Stokes equation. Now, when we need to have a transient solution, or you want to make a movie by recording the change in your variables involved in a computational domain, then we need to go with the unsteady solution, and then we need to take this full form for the solution. So again, I'm telling you the first one is unsteady term, and this will be the advection. This is a source term, and this is a diffusion term. And origination, you already uh, I think you studied in your UG label and PG label how to drive them. So further, how to discretize them, I'm discussing today. So this variable, and the most important thing is in the solution what are the problems, and how to deals with them, that I am covering today. The first thing is, in a same x momentum, we have one variable as u and another variable as p. So if I solve this problem, and if you as a user will be interested to obtain both velocity and pressure from a same computational domain, then you need to solve u and p as well. So now in the same equation, they both unknowns are available. So it is not possible for us to solve them. Then we need to use some iterative approach using following some algorithm. For that, the most famous one is simple algorithm that I will discuss toward the end of the lecture. So we generally what we do, we discretize this first order differential, second order differential for u velocity considering the time level, and then solve this equation for x and y, and later we obtain u velocity and v velocity, and then pressure from a different approach separately for a problem. Driving depending upon the velocities that obtained at the previous level. So generally this is the way how we discretize, or how we generate a mesh to a computational domain. Computational domain, I mean to say, a fluid flow problem, a flow through a channel or flow through a pipe, like say we can take an example. So this is the way how we can assign the nodes to uh, computational domain, where blue ones are showing you the boundary nodes, green one are just the border nodes, and yellow ones are the inner nodes. So we generally to telling when you are maybe using any NC software, so there are some boundary condition you earlier naming them, like in the meshing inlet outlet whatever, or wall as insulated or symmetry or open. So pressure maybe you assigning, then where will be assigning the values, you will be assigning them at the blue circles. Okay, and taking their reference inside, we will be solving them using the discretized form of these equations. So now it means that these equations, when it will be solved for u and this will be solved for v, let's say, then that algebraic form will be applied to a single grid. They will be giving you value for a single grid depending upon a time marching scheme although. So all these equations will be solving for individual grid points. So I think you will be familiar with this grid point what I'm using. So we call in the mesh a grid. You can say a square as a grid, and then at the center that will be a grid point, or cell center also we call it. So for continuation now, how to discretize it. So I'm telling a new approach for through finite volume method, which is very simple to understand. As the way we write the differential form of the equations, the same way we will follow the steps, and we will be writing the differential discretized form for the differential equations. For continuity equation, what we do, we generally do the mass balance, mass entering on a control surface, mass leaving to a control surface, to ensure the check whether the same mass is coming in or out. So the similar way it will be written for the various phases. So you will be seeing in my upcoming slides also these words like w, n, e, and s. So w will be representing you the west pole, e will be the east pole, and be the north, s will be the south. So these are generally used to indicate you the the directions, and accordingly how the fluxes will be presenting in a particular direction. So P, this will be the cell center. So I'm using P, to symbolize it. So transport equations like say. So before to go to the x momentum, y momentum further, in the very beginning, the first term will be, unstudied term. So this is the common way to discretize it with respect to the time level. Uh, and where delta t will be representing you time step, and this will be representing you the next time level. This will be the previous time level. Okay, so this representation will be common, although you will be using any implicit scheme or any explicit scheme, uh, except the Crank-Nicolson, Crank-Nicolson trapezoidal rule. So this representation will be common for explicit implicit method to discretize the unstudied term. So what we do, we first assign a variable to a cell center, as I showed you in the previous slide. At the center of a control volume, P will be represented. So any variable, whether it is a velocity, it is a temperature, we will be using P at the cell center. We will first assign any variable at the cell center, and then we will do temporal, evaluation with the advected variables or diffusive variables, and then we solve our equation for a particular variable with respect to the next time level. So this is a discretization for the unstudied term. Now we have second term, which is advection term, that involve like rho u del u by del x, rho v del u by del y for x momentum, like. So how it will be discretized? So we will consider here, for a control volume, momentum flux is entering from a control surface and leaving from a control surface. So these red symbols I am representing with the fluxes which is entering and entering from a control surface or leaving from a control surface in a particular direction. Like say from west side, from east side, from south is entering, from north it is leaving. So the same way, we will further utilize some advection schemes for their solution. So you must remember, for the discretization of advection term in x momentum, the momentum flux which is entering to a control surface, leaving from a control surface. Similarly, in y direction, in x momentum, I think you will be well aware velocity will be function of x and y both coordinates, and representing change in only a single direction with respect to two variables. Okay. So similarly, in the y direction, the point will be now how to calculate them further, that I will discuss when I will show you some advection schemes. Not much in detail because we have another expert who will be going much, who will be in much detail representing you the advection schemes. But now, to make a discretization of advection term, I am telling you we will be writing the momentum flux outflow minus inflow uh, in terms of the other variables only. That will be the momentum flux leaving, and this is the momentum flux entering. So and likewise we will left them, and later to find their value at this location, we will be applying some advection schemes. So what we did at present, I can use one coefficient representation to represent the momentum flux, advection flux on a face of a control volume. Then momentum flux on a momentum conservation can be written like this. And where I want to using the same representation for energy equation, I can use it. Where enthalpy, enthalpy flux entering and leaving in energy conservation. So there will be the two levels in advection again. First, we will represent a variable to a cell center, and then we will apply some advection schemes to calculate them. So they also will be called as two-level schemes. So this is just a brief about the advection schemes, but problem will arise in a solution if you will be now familiar with these symbols and these cell centers, yellow cell centers. Let me show you on one of the picture here. Let's say you want to obtain one value at the cell center, then, or let's say at this green cell center, then this at this boundary one value for your reference in the form of a boundary condition is already assigned. Okay, so by taking reference of this value, we have to calculate one value at this cell center. When we are moving in x direction by assigning one value to each of the cell, considering explicit method. Then for this cell center we need to make use of this value or maybe this value. So we will assign some weightage because we don't have any, you know everywhere there will be the initial value. Because fluid flow problem, fluid will be, let's say, coming from left to right. So you will only assign one velocity, let's say u velocity at this boundary, and you will be unknown with the velocity value everywhere in the computational domain, even at the outlet. So there will be no any reference to calculate a value at the grid point in a particular direction. So what we do, by considering the weightage function, weightage to a particular previous to the previous grid, neighbor grid, and a boundary grid, we will be augmenting inside. So this approach I am just going to tell you now. So let's say a fluid is flowing in this direction, then there arise upstream and downstream. So upstream will be the wake of the fluid, and then downstream coming in the forward. Let's say when a river is flowing, then upstream and downstream you can properly understood from a, let's say, from a mountain. So this will be a cell center. This will be a location at the center of these two cell centers where we are interested to find out the fluxes. Because now if I create a cell there, then this will be the point where later we want to update a value by considering the value of the flux which is entering at this phase. So for this particularly, at this particular point, we will be using some advection schemes, like say FOU, first order of bind, then second order of bind, then center differencing we have, then quick scheme we have. So what we do in all, we assign weightage to the neighbor cell centers. So let's say fluid is flowing from left to right, and we are interested to calculate a value at this particular location, which is a flux location. So we will assign 100% weightage to the previous cell center location. So 100% weightage has been given to this one, and a flux will be calculated here, which will be later involved in solution of unsteady form, and give you updated value at the cell center. So similarly, for a second order upwind scheme, we consider two upwind and upwind of upwind cell center, means two previous cell neighbor cell centers, and assign different weightage to them. And then accordingly, we will find a value at the for the flux, momentum flux. That will be a intermediate location between the two cell centers, or a phase center location for a control volume. Similarly, we have CD, where average is assigned one downstream and upstream. Their average is assigned to calculate a particular variable. And same approach is also followed, in energy equation for temperature to calculate temperature fluxes, enthalpy fluxes, and similarly here for momentum fluxes. And likewise for quick, we assign different weightage to upstream and upstream of upstream, and also involve one downstream cell center to give a weightage. And accordingly, a particular variable will be calculated. So this is a brief about the advection schemes. And then uh, till now, I told you how to discretize a unstudied term, temporal term, and how to discretize which is a second term, which is advection term. So in advection term, we simply say that uh, the way we derived them, the momentum flux, leaving and entering to a control volume, to have estimation of momentum lost in a fluid flow problem. And during this process, we will be taking a two label approach, where first time in the first label we assign cell center with a particular variable, and then in the second label we will make use of advection schemes, and update the value at the same cell center where we earlier assigned them. So now this is the diffusion term, which arises from the viscous forces involved in the fluid flow. And uh, as I told you, momentum transport uh, in a fluid flow problem in two ways. or in the combination of two forms, two momentum transports or their modes. One will be diffusion, another will be advection. In advection, we only consider the bulk moment or bulk or macroscopic motion of the fluid, and for that one term that arises, and for that I already have told you how to discretize them, which is the advection term. And now there is a diffusion term where macroscopic momentum transport or energy transfer will take place. And for a fluid flow problem, that region will be near to the boundary or near to a wall where boundary layer forms. So we consider in the particularly in the boundary layer that the momentum or energy transport due to the molecular motion because of their random motion. So there particularly, the viscous forces also, have their major, significance effect in the origination of the boundary layer. And for a fluid flow problem, when we make a plot across the flow, then you already first a parabolic curve will form, and taking to a maxima at the center if I'm talking about a positively flow, or for a fully developed flow, then a complete parabolic profile will be formed in the flow. So reason is near to the wall there is some viscous forces and shear factor that dominates, and there will be no slip that we consider mathematically. From a zero, velocity will start increasing and attaining maximum at the center, and same is replicated to the top wall also. So a parabola is generally formed for the velocity profile in case of fully developed flow. So so we consider in the within the boundary layer. So flow is dominated and rotational, and generally dominated with the the shear effect and viscosity, which is the fluid property. So for that particularly, if you remember the differential form that originates mu del square u by del x square or plus del square u by del y square for x momentum, similarly it is for y momentum. So how to discretize them? So force is when, again, for a control volume, because this is also originated from a conservation form. For control volume, let's say the force, if pressure will be applied on a control volume, then against the pressure internal resisting forces also will occur. One approach, as I think you already are well aware, in CFD what we are considering, deformation of the control volume is not considered. So in order to avoid the deformation, so the pressure or the pressure forces which is arised in the fluid flow on a control volume, they all has to be balanced. So we are using normal and shear vectors to normalize them, to nullify the effect of the pressure forces on a control volume. So there it gives a reason to normal and shear forces for a control surface. So now there again, for the solution of these second order differential equation or the diffusion term, we need to again go for the second two label approach. In the first label, we again consider assignment of a variable to a particular cell center, and the second label, what we do, we consider some subsidiary laws and use their mathematical form here, like say Newton's law of viscosity has been presented to you. And in the second label, we will write these subsidiary laws before to come the derived form, which is second order differential, will in x and y direction. And this approach we do using the Fourier law of heat conduction in conduction heat transfer. So in diffusion and in the discretization, two level approach will be considered, and again these forces will be balanced, like say in x direction. So if I consider their balance, then this will be in the opposite direction to the x, consider as minus, and this will be in the positive direction, so consider as positive, again likewise they also will be treated in the same direction. We'll put sigma xx sigma yx using subsidiary law in the equation, and it will give us one discretized differential form in the second level. So that we do in discretization of diffusion fluxes, diffusion terms, two level approximation. And then this is piecewise linear approach that we generally call, where in the second level approximation, I told you these variables, let's say in the form of forces, they will be replaced with some subsidiary law, and then subsidiary laws, let's say sigma xx, this is a location, then it will be written in the form of p and w, like say it is written here. Similarly, this is the flux, diffusion flux here, then it will be written in the form of p and e, like we do for like say Fourier's law of heat conduction, when we have to find out the total heat transfer considering the temperature difference at a particular delta x, like say in x direction delta x distance, then we consider 2 points, let's say outlet minus inlet multiplied minus thermal conductivity divided by delta x. Likewise, in the we have subsidiary law, Newton's law of viscosity, that will be used here to represent the discretization approach for the diffusion terms. Similarly, in the x direction and y direction, we call that piecewise linear approximation. Although there are some other approximation approaches are available in the literature. So now this is overall what we did with the diffusion term. Again, we will make a balance again for a control volume, and the fluxes which are leaving and entering, they will be balanced, and in the second level approximation, fluxes will be replaced with the subsidiary laws, and they will be applied for a finite locations, and we are able to linearize them in form of variables. And this is for the source term. So pressure is applied on control volume in x direction, because we have for pressure a first order differential only. So pressure in x direction, we will simply balance it in the x direction. This is a positive direction, this is a negative direction. Okay, accordingly we will write them in the form of fluxes. And where I told you earlier, the most difficult thing is in this fluid flow problem is in the same equation, let's say for x momentum, two variables arise, two unknowns has been arisen. One is velocity itself, and another is pressure. And if you are interested to calculate pressure also, then if you solve that whole equation for pressure, then you will not able to get any velocity. If you solve it for the velocity, then you will be remain with the one unknown, that is pressure. So there comes the need of algorithm that is given by S.P. Pathankar, one of the Indian, and who particularly originated the simple algorithm, and that will be applicable then for their solution. So pressure discretization in the y direction. So we will balance them in a particular direction, and we'll write them in the balanced form like pressure on the west face and pressure in the east face, like the pressure in the pressure force in the and that is entering in the south face and leaving from north face. And now collectively, what exercise we have done for individual term, uh, we will write now, let's say for x momentum, we'll write its discretized form in this way, where this first term is correspond to unstudied term. Uh, Dr. Knows I'm audible, or anybody from audience, please let me know I'm audible or not.
Sir, audible.
Okay, okay. So for x momentum, now this is the form we have. First, I told you unstudied term. Second is advection. Third is diffusion, and fourth one is a source term. So I told you whether you are using any implicit or explicit scheme, the way to represent the unstudied term will remain same, where P will be cell center and n plus 1 be the next time level, n will be the previous time level, or you can say if you are just starting the iteration, then n representing the initial level, n plus 1 the first iteration at an increment of delta t in the time. So this is the way to represent it actually. So when I will have the all variables available at n level, then I will be able to update using explicit method one value at the same cell center at the next time level. I think it is sometimes it is difficult to digest, for the beginners. For their reference, I'm telling again, we are simply considering the way we derived the equations, uh, differential equations at UG level, considering the control volume approach. And this representation is also familiar with the same thing. Consider it is a control volume, and we want to update value at the cell center, because in finite volume method we do the averaging, surface averaging for a variable, and assign its value at the cell center, where for let's say for finite difference methods we obtain the values of a variable at the nodes. Okay, so for a control volume, what we consider, the fluxes or forces, they are coming from a control surface, entering from a control surface and leaving from a control surface. As we do energy balance, let's say energy entering to a system, leaving a system, what it do, it let change inside the system. Same theory has been adopted here also to represent you, to make finite volume method very easy to understand. Although in many books integral form it represent you in a very difficult way, and it looks very difficult to understand. So these are red triangles, rectangles representing you actually the fluxes, wall fluxes. It can be anything like momentum flux, it can be the pressure flux or force, I can say directly. Okay, so we generally in this equation we call this advection flux and diffusion flux and switches. So now come to the advection term. I told you in advection, momentum entering here in terms of force we write it. The force which is representing the momentum entering inside a control volume, leaving a control volume. But you must remember that when we will be deriving this advection term, so overall material derivative has been represented, or Eulerian form has been represented by taking a variable which is a function of x, y, and time. So that give you, by applying a Taylor series or by applying a chain rule, this this collective unstudy plus advection term. So I think you will be well familiar with this all derivation. In a similar way now, in a x momentum we will be having one variable with respect to two coordinates, x and y. So this is a representation of the same. Whether we are augmenting in x direction, we also having the effect of for the variable in the y direction as well. Similarly, when there will be y momentum, you will be getting like differential like rho v del v by del x plus rho v del rho u del v by del y likewise. So in advection, I told you we need to calculate these advection fluxes at these locations, and we are absent with any reference of the some velocity values inside the computational domain, because what we considered in a fluid flow problem, flow is coming from left to right or from right to left, from top to bottom or bottom to top, any of the direction you can assume, depending upon whether the gravity will be applied or not. Okay, so let's consider the fluid coming from left to right. Then you will assign a boundary condition at the left wall. So there we will having some value, fixed value like 2 meter per second for the velocity in x direction. Considering the reference of that velocity, we need to update the value inside the control volume. That is our overall interest. As I showed you some of the animations earlier, everywhere there will be some boundaries, and changes are occurring inside the control volume. So when you want to record the movie, then you want to see the changes with respect to time happening inside the control volume. So For that, what approach has to be adopted? Mathematical approach has to be adopted. We need to make reference of the boundary conditions, and accordingly we need to update the value inside. So for that, for advection, we need to make use of some interpolation and extrapolation schemes like FOU, SOU. They are extrapolation schemes, and then we have CD, then quick. They are interpolation schemes, I think, and they are also available in the solvers. I think the guys who are working with ANSYS Fluent. So when you set up your problem, so there you will find what treatment has to given to momentum and energy equation. Then we update generally with the knowing the relevance from first order to second order upwind. So that approaches has to be used here, assigning weightage to a particular cell centers by taking the reference like upstream, upstream of upstream, or downstream, and assigning them weightage. We will be calculating these advection fluxes at these centers, and later we will put their discretized form here, and their value will be coming from from by assigning some weightage to the boundary values. So we will be later getting the value for this variable for the next time level, because this equation and study term will be rearranged for UP n plus 1 only, and all terms which are here, they will be taken to the right side of the equation. So and if advection will be solved, so it will be augment only in the UP value. So collectively we will be getting the value for UP when diffusion term also will be solved. So for diffusion, I also told you that again two label approach, linear piecewise approach we also called it. We have the stresses, interresisting forces against the pressure. We can consider, let's say, pressure coming on the faces. So against them we need to balance them without deforming the control volume. That is the one assumption we generally take here. So this has to be calculated by making use of subsidiary law. Let's say for balance in the x direction, let's say I'm getting the variable this sigma xx and sigma yx, sigma yx. So I have I have differential formula label for the sigma from the Newton's law of viscosity. I will simply replace the sigma with mu del u by del x or mu del u by del y, and that will be represented explicitly for a delta x or delta y uh, distance between the two cell centers, and that will value will be this term will be discretized likewise for the pressure terms also. We will only do the pressure balance, and we'll write the discretized form for the source term. So this is the way how we discretize x momentum. Similarly, we will discretize y momentum for unstudy problem. For a study problem, this term unstudy will be 0, and we will only having these variables equal to the pressure. So what we do there generally, we collect the advection diffusion and make them equal to the pressure that we generally do in the steady state problems. But when you want a movie, you want to represent change of variable with respect to time, then you need to solve that for UPN plus 1. And a similar way also for energy, we have similar equations, similar terms like advection, diffusion, and source terms available in the equation, and we solve there for temperature at cell center for the next time level. Now I'm going to discuss with you the staggered grid, because before to discuss the staggered grid, there is a need to define the difficulties to assign the locations to the various variables that arise in the fluid flow problems. So as you know, till now I told you how to discretize a individual term that comes in in the differential form of x momentum equation or y momentum equation. that is unsteady, and then advection, diffusion, and then source, which is pressure term. But now we have three variables with that we have to work now. And the problem that arise, I told you earlier one grid structure, which is the computational grid structure where we divide the computational domain using horizontal and vertical lines and created some orthogonal grids where each grid I was representing also with the control volumes to give you the thermodynamics, understanding of the problem of the fluid flow and the various physics associated with it. The problem now arises, we are only considering yellow circles which are representing the cell centers. But now we have to deal with three variables, which is u velocity, v velocity, and pressure that we generally obtain after after the solution from a fluid flow problem, that is u velocity, v velocity, and pressure. But now at the same common point, which is represented you with the cell center and yellow circle earlier, all three cannot be assigned at the same location. If we are assigning them the same location, then after taking iteration, they all will be replacing with each other. So we will not be getting any u value, any v value, or any p value. So which of the variable you later define in the code, that only will be represented there, and false values will be coming in the solution. I hope you will be understanding this. To give you the understanding of what I am trying to say is, in this equation, if you see, there is no relevance of this continued equation till now. We will keep this continued equation for later to make a check over the velocities that we are originating from x momentum, y momentum for u and v. On the basis of that, for a control volume, we will only make a check by multiplying rho ab, whether the mass which is entering to a control volume, same mass is leaving or not, or maybe satisfying the convergence criteria that you have been set for your problem. So for x momentum, tell you that if I will be solving for u, then where this p will be assigned, because p for p, a separate location should be there in the code, in the computational domain. From there I can get this value p to my equation for the u. Okay, for the first instance, let's say what I will do, I never told you we will rearrange the equation for pressure. I told you in the whole discretization we will discretize the all differential equations for u variable only. Similarly here for v, so where p will also be present in the differential, in the discretized form in the same equation, and will be one unknown for us. So uh, if I will assign a location for u, then p must be presented separately and v must be represented separately, because in a solution of x momentum I need also the value of v in the direction where we have uh, rho v del u by del y. So here we need v as a value to solve the whole equation for u velocity. Similarly, when I will be solving for v, then I must have this value of u. So now try to imagine in a mathematical way, I need to keep these equations separately so that I can algebraically solve equation for a particular variable by getting the value from a separate equation for let's say for v or p. If I'm talking about x momentum, I'm solving for u, then from a separate equation uh, I must be getting v and I must be getting p. But for a grid representation, so they also need to be assigned different locations. I hope I am able to make my point clear. So for that we need to do staggering approach, which is called as staggered grid as approach. So this is a grid representation, as I earlier showed to you, where blue circles are representing the grid points. A boundary, a boundary boundary grid points, where just inside we generally represent with the border nodes, and the remaining ones will be called as inner nodes. These border nodes having particular significance while you write the code that I'm not discussing. So here to avoid the confusion, I'm only making boundary nodes and the inner nodes. So I am telling you, if this at this particular location, I am assigning this location to u variable or v variable or p variable, then we are not getting any of the value, neither for u, v or p. So we need to assign them at a different locations. So for that, we come up with the idea of staggered grid. So here I am representing you one very common, or one standard problem. While you will be writing a code or to make a solver for fluid flow problems, then we generally at a for a laminar flow or turbulent flow, we generally validate our problem, our numerical solution with the lead driven cavity as a case. There we consider generally a lead is capped over enclosure, water enclosure, or any fluid enclosure, and it is moving with a particular velocity in x direction, let's say. Because of that, some changes will occur inside, in the fluid domain, and various boundary conditions will be assigned to the remaining three walls, where we will assign here particular velocity, all these boundary nodes, and there will be no slip, no slip, no slip. And for this problem, I am telling you the staggered grid. So here, u velocity, I'm using green scare to represent you the location of the u velocity. Red triangle I'm using to represent you the v velocity, and the yellow circle I'm using to represent you the scalar which is pressure at the center. So just consider, let's say, this particular cell or grid, where this yellow one is a pressure and this green one is representing you the location of the u velocity, and this red one is representing you the location of v velocity. Now this is actually the staggered grid approach. Now we assigned them different locations. What will be the advantage of this assigning of these locations is, when you have to apply continuity later on, so this in the x direction, this location will give updating the value of u by simply multiplying with rho into a. You will be getting the mass as a force, and you are able to make a check whether the same is coming or same is leaving or not. Okay. Similarly in the y direction with respect to the v as a variable, and at the same time we will be having the three matrices. Three matrix, one is for u, v and p. They are originated at the different locations, so it will be easy for us in a code to make use of uh, the u and p variables, let's say for a calculation of u velocity in one go. So this is the approach only. So where I separately present you these cell centers for u, v and p, then I told you just for the previous in example, just consider neighbor cell centers. Let's say I am considering this cell with my neighbors, this cell p with my neighbors, west side neighbor, east side neighbor, north and west. So that I'm presenting you in the next slide, where p is the center. It's a west neighbor, east neighbor, south and north. Then I told you green one, it is showing you the cell center for the u velocity. The red triangle is representing you the location for the v velocity. Now this is the location for the pressure. So if I consider for the u, which as okay, first consider for the p. So let's say I taken separately for the p a cell center and representing you here. You follow my cursor then. So if p is resting at the center, then on the we are getting on its control surfaces, u velocities and v velocities. Where if I create a cell center for u velocity and representing u separately, then its a cell center is involving velocities at its corners, and which velocities? V velocities at its corners, and pressure at the phase centers, and which is also actually required in the solution of the discretized form of the u velocity. Because if you remember the discretized form of a u, it is involving your v variable as well, and pressures in a particular direction, x direction, minus del p del x, if you remember source term, which we discretized to involve only the two cell center values, so which is represented here to include them in the solution of u velocity. And similarly for v, we need to get the value of u velocity, as its advection term involve u variable, wherein the advection form of v, u velocity, it involves v velocity. So we will be getting updates for the u velocity from these coordinates, where pressure is represented in the del p by del y in the vertical direction. So this is actually a staggered grid approach. So just to give each variable different location and involve other unknowns in the neighborhood, so that in the code when we will be writing them, we can get updated value for each of the unknown for a in the equation of a variable. So this is the way how we discretize earlier. We already understand this, and this is again the recapitulation. We are moving toward the end of the slides, uh, where I told you for the mass continuity equation, we use this equation to make a check over the values which are coming from the solution of momentum equation for u and v velocities. So u velocity, if it will be rising here, then it will be easy for us to make a mass check by simply multiplying with rho and area, and it will be telling us whether our solution is converging as per the error that you have set in the for your problem. Then uh, for your transport equation, x momentum and y momentum, let's say for x momentum, this is the discretized form for unsteady term, where for a single u velocity we will be getting the pressure and our unknown v velocity in the equation. Similarly for v variable, we are getting unknown u in the advection term, so we will be getting update value of this one and pressure. And similarly for temperature, if you have to solve the energy equation as well in conjunction with the momentum equation, then the values which are raised coming from the momentum equation, they will be given to the advection term of the energy equation to solve, like say u del t by del x plus v del t by del y. Okay, so making it simple to you, I'm this we already have covered. So here, for this particular, when we will dealing with the advection term, I told you we need to calculate the advection fluxes. For that, advection schemes will be used for x and y, similarly for energy equation. And where for diffusion term, I told you we will be getting like say sigma xx and sigma yx. So using the subsidiary law in a two label approach, linear piecewise approach, we will be replacing the variable, let's say sigma xx, with the Newton's law of viscosity, and we can write them likewise. And each variable will be replaced using this form, and that will be giving us the discretized form of the diffusion equation. So after discretizing each of the variable, let's say for pressure, we already discussed this. This is the final form where we will solve this equation for upn plus 1 and take all the term on the right hand side, and where right hand side will remain with unknown pressure and velocity v velocity. And this is the way how the various forms will be rising in the code. This one for v velocity, So now there comes now the solution of the uh, Navier-Stokes equation, and the approach that we use is called as semi-explicit or semi-implicit approach. So I'm telling you semi-explicit method today, and later one algorithm for semi-implicit method also will be shown to you. So there will be only one difference in explicit and implicit method. So for explicit method, some known and some unknown. Let's say some at n label will, some terms will be used at n label and some will be used at n plus 1 label in semi explicit method. Although in full explicit method, what happens? We take actually one variable at n plus 1 label and all other variables on n label. So it will be very easy for us to find the solution, because in the first iteration, the value of the variables at n level will be available from initial value, and that will give one increment directly to the n plus 1. But here, in the numerical solution of a fluid flow problem or Navier-Stokes equation, we again come up with another difficulty, which is actually the source term. Uh, if I will solve this explicitly for upn plus 1 only and take all terms on the right hand side, then you should not forget as p u, which is pressure force in the x direction, it is unknown. For unknown, we need to assign n plus label to that, because its value from nowhere can be identified. So n plus 1 has to be assigned, because this value also has to be updated in the solution. Then only when, if I will be solving advection, then I need pressure. When I will be solving diffusion, then I need pressure. Okay, because they are making the reference of pressure as cell centers. So this value also will remain unknown. So I cannot say now my method can be a full explicit method. So there is an approach now, semi explicit or semi implicit method. And although there are also pressure uh, coupling with the velocity or pressure decoupling, also there are some approaches. We are coming with the pressure coupling as approach. So now in semi-explicit method, where I cleared the point that for the solution of Navier-Stokes equation, we cannot make our the differential form, discretized form, at a full explicit method, a full explicit level, because there p which is coming in the equation is unknown to us. If it will be known to us at some level, then we can, let's say at initial level, then we can uh, you know or at some particular boundary, if it will be known to us, then we can make a reference of it. If you are well aware with the pressure as a boundary condition to a fluid flow problem, then or you may be using any CFD tool, then what we assign the boundary condition for pressure, we straightway go to the outlet and assign pressure P is equal to 0 as a boundary condition there. And then uh, for other remaining balls, three balls for a 2D problem, then we apply pressure gradient equal to 0 at these balls. So one mathematical form, let's say del p by del x equal to 0, if you discretize it using any, let's say for a finite difference method, then it represent you difference between the two grid points at a particular, let's say extent, delta x or delta y is equal to 0. It means at that wall particularly, what are the value calculated inside just at the border node, that value has to assign to the boundary node, because there is no reference of the pressure at the boundary, because we are unknown with the pressure value at the boundaries, except p is equal to 0 at the outlet boundary. So, and we also know that, for a fluid flow, there must be pressure gradient. So pressure must also be, at the inlet for pressure, you have a pressure gradient as a boundary condition. It means that the pressure which is inside, means at the border node, that value has to given to the boundary node. at the inlet where you are assigning velocity with some finite value, let's say 1 meter per second. So we have to make pressure a function of velocities also, so that by taking reference of the some velocity values, pressure can be calculated. Because uh, pressure must be high at the inlet and 0 it is approaching toward the bottom, toward the outlet, following some gradient without any equation for the pressure. So that is the illusion actually. So we have come up with the semi-explicit method where I'm writing you the original proposition, where this is the unstudied term. I think now you will be well aware of in this form, uh, unstudied term. This is advection, this is the source term, and this is the diffusion term. And for this advection term, I told you we need to calculate the momentum fluxes based upon the advection schemes. And for diffusion, we need to make use of two label approaches, piecewise linear approach where we will be making use of subsidiary law, Newton's law of viscosity, to give the discretized form of the diffusion term. And now, in original proposition, if you uh, observe how many unknowns we have this up n plus 1, which is of our interest to know the velocity at the next time level. This pressure is unknown, we cannot calculate it. And in advection there will be v velocity, and in diffusion we will having the reference of the values at initial level. So what we do in the semi explicit or semi implicit method, which is simple method, simple algorithm as well, semi implicit method for pressure linking equations, what we do, we follow one step: predictor step and corrector step. In predictor step, what we do, you need to replace, I'm telling you very easy way to understand this all and to remember. What we do in the original proposition, whatever the values are available at n plus 1, we will replace them with the n label. And to make different to make a predictor equation, one step has to be follow. Up n plus 1, we will write it like up star, and p at n plus 1, which is unknown, we will take it to the pn, and means initial value or one previous value. So I will be saying initial value because let's say when your code has to start doing iteration, it needs some initial value in the beginning. So for initial value, for fluid flow problem, we assign u velocity, v velocity, and pressure everywhere 0 inside the computational domain. If pressure gradient is not known to you earlier and you want to predict the pressure everywhere inside the computational domain, then so pressure will be assigned 0, u will be 0, v will be 0. As I told you, as I show you when I will open setup in the ANSYS Fluent, then same things will also be clear to you. So now, by doing this predictor step, I am just replacing upn plus 1 with up star. So that I will keep as unknown in this predictor step. And this upn, where n is taken, it means these values are available initially. So this p will be available you initially, p will be 0, this p will be 0. Everywhere at every grid point, this p will be assigned some value, so it will be 0. Let's say for p at this location, at this yellow circles, this west it will be 0, east will be 0, so this value will be 0. And for diffusion, we'll also take reference of the velocity values at initial level. And for advection also, we will be assigning some weightage, and accordingly we will be taking the value for our velocities. So we will be just heading with the one step. I'm telling you the solution for x momentum only. Similarly, it will be goes for y momentum. So now I will be having now up star with some numerical value now, which is calculated by taking the value of the variables at a n level, at initial level. Now we are proceeding toward the correction step. In the correction step, what I will call as a correction step, the sum of these two equation, not sum, but I will subtract, the predictor step from the original proposition. That will be called as the corrector step. So I will call this corrector step as up prime. So p prime I'm using to represent corrector step, which is the subtraction of predictor step from the original proposition. So I'm representing it for in a study in a unstudied term like upn plus 1 minus up star, which is original proposition, and this is predictor step. So in correction step, you will be having now up star as a numerical value, which is calculated by taking the reference of the all variable at their initial level. And what left now, upn plus 1, it is still unknown. If I'm going on the right hand side, so I will be keeping them as like, and taking only some mathematical rearrangements or formulations on right hand side. So how I will write it: pp, again predictor step for pressure, the correction step for pressure at p point and for east point, p at n plus 1 minus p at n level. Similarly for at east point, pn plus 1 minus pn. So this is correction I am doing in the pressure side. So this p at n or pe at n, they both are available numerically now from the predictor step, or you can take directly the reference of the initial value which are available for ppn or pen. So again I left with pn plus 1. Still I am not getting its value. Until I am not getting the value of p, this equation cannot be solved. Means new value for upn plus 1 cannot be solved. So what I do uh, in the corrector step, I predict the value of pressure from two methods. So that I will show you. And similarly for y momentum equation, this is the original proposition. Again, we have in original proposition, we want to solve this equation for up n plus 1. And again, the problem that arise, we have unknown p at n plus 1, p at n plus 1 at two grid locations, so cannot be solved. So we go to the predictor step. In the predictor step, what we do, we'll replace p n plus 1 with p star, and all these values will all these uh, values will be calculated by taking the reference of the variable at n level. And I will be getting some at the end of predictor step, I will having some numerical value available for vp star. And in the correction step, what I will do, I will subtract original and original proposition with the predictor step that I'm writing here. Similarly on the left hand side and right hand side. So what again, what I left with vpn plus 1 because of pn plus 1. So now there is a need to predict some value for the pressure. Without the value of pressure, we cannot, proceed further and update the value of u and p in the computational domain. So now there are two methods: pressure correction method and pressure projection method. In pressure projection method, what we do, we make use of the Poisson equation, that is a function of some first order differential for the velocity variable. And in pressure correction method, what we do generally, first we assume any value of the pressure. Let's say I'm assuming the first instance p n plus 1, I'm using 1 atmosphere. By only considering p at 1 atmosphere, what happens, I will be getting the value of this variable, so that I'm predicting actually. I just used one value, 1 atmosphere for this p n plus 1, and similarly for p n plus 1. So I will be getting some value now. So I will rearrange now this corrector step for vpn plus 1, where vp I will be now with some numerical value, vp star again I will be having some numerical value from the predictor step, and I will be getting vpn plus 1 as a new value now. Here I think sometimes there is a difficulty to understand. The point is, character type I'm writing vp prime only, don't consider this one. which is mathematically equal to vp n plus 1 minus vp star. Or on the right hand side now, if I predict this value, let's say this is a guess, or 1 atmosphere pressure I'm considering. This I already have calculated from my initial value. Let's say p is 0 initially. So I will be having this p prime and p n prime. So I will be now having some numerical value available for vp prime. So rearranging this equation for vp n plus 1, I can write vp n plus 1 is equal to vp star plus vp prime. And then I will be getting new value for my velocities. This is the way how we solve actually for fluid flow problems, uh, and solve them for for u and v velocity. So let's say now you are able to get the new value for u velocity and v velocity at n plus 1 label. Again we will go for the predictor step now. Now this value is available, this value is available to you now. So now what we do again in the predictor step, the new value that you calculated by taking the pressure as a guess, they will be now considered as uh, at n plus 1. They will consider at n level now, and we go to the predictor step now. So again they will be the new guessed value. Let's say 1 atmosphere pressure we calculated earlier na? Because p will be 0, let's say in the first instance. So they will be now considered here, and likewise we'll proceed for the correction step. And then again we write this corrector step now, rearrange this for upn plus 1. Again we make guess for the pressure. Let's say for the second instance, in the first instance, let's say the pressure of 1 atmosphere has been considered. Then from a continuity equation we make a check that 1 kg per second is entering to the control volume in the from the west side and from the south side. But by making calculation of the new value that is coming for u and v velocity, it is 2 kg per second. So momentum equation will continuity equation will not converge by considering this pressure value as a guess. So we need to go for another value of the pressure. We will keep on doing this step until we are not getting continuity converged. It means that when for a particular certain error, for the mass which is entering and leaving, we are not approaching up to that level. So we are keep on guessing the value for the pressure. So this will be the step in the pressure correction method, wherein the another one pressure projection method, there is a equation considering some relaxation factor that is implemented in your CFD solver. So that will be used, and we will be predicting the value for u and v velocity, and similarly for pressure. So this be done in the from the for the velocity after corrector step. So this is unknown. So we rearrange. This is predictor step. This is corrector step. In the predictor step, we consider all the value of the unknown variables at n level. N level means at their initial level, their initial values. And in the correction step, what we did, we assume pressure for computational domain. So now both are available, so we can get a new value for the velocity. Similarly, in the for the v velocity, and this is we are doing in the pressure correction. This p new p at n plus 1 has to be calculated. So this is already pressure at initially that you assign to the computational domain, that we generally do pressure p is equal to 0 at all cell centers. And this is the new value for pressure you guessed for to just start with the computation procedure. And we are keep on doing this until continuity has not been satisfied to a particular level of the error. So in continuity we are making a check, and again we are keep on doing the calculation until solution is not converged. And this is now the simple algorithm. You will not find any difference in the way we are doing in the semi explicit method. What we do generally there in semi implicit method, we make uh, equation for all variables in one go, because I already told you we need to make in implicit method all equation at n level. So they will be taken, and some matrix solution method like say Gauss seidel method has to be used when some metric solution has to be given for in one way you want to calculate UVP, and similarly you can uh, use these algorithm for at advanced level when turbulence problem has to be solved. So I'm presenting you here also the same algorithm when you need to calculate uh, k epsilon values in turbulence problem. So that's all from my side. So before to end the lecture, I'm just going to show you one setup in ANSYS Fluent. Okay. At the meantime, if you have any question related to the the discussion that we had and through the lecture, you can ask some question. As I understand, in one go, it is very difficult to digest everything. There are so many mathematical forms and way of discretization, and finally they come to an end using staggered grid approach. There are other approaches as well, but this is one of the famous one, commonly used, easy to understand, also easy to apply as well. And then be semi-explicit method, semi-implicit method, any of the method you can adopt, and you may have the solution for your fluid flow problem. So I think everyone will familiar with this, ANSYS Fluent. So whatever we have studied in today's lecture, I'm just want to show you this all, in a computational tool, CFD tool we call them, CA software. At the meantime, if you have any question, any doubt, you can ask me. Okay, so I'm considering a rectangular flow problem, considering any random dimension for this. Okay, I'm done with the geometry. So random dimensions I have considered just to show you one fluid flow problem. Dr. Manoj, I am audible, or anyone from audience?
Uh, yes, sir. Audible, sir.
Okay, okay, fine. So for such problem, I generally go for edge meshing, edge sizing. Okay, fine. I think you already had a lecture on meshing, so I'm not going to discuss mesh techniques in detail. So just showing you, I'm going to create a structured mesh, structured orthogonal mesh. Okay, so you can make a quality check as well from statics. But for such problems, uh, we need to check orthogonality. So it will be 1. So 100% orthogonal mesh we have created. You can also check the stat min or max. So 100% is there, means everywhere we have orthogonal mesh. 90-degree angle is created between the elements. So now I need to name them. So I will select the edges for 2D problem. Okay, fine. But as per the problem is concerned, for a duct flow or for a pipe flow or a flow through a rectangular or any of the shape, because of the no slip boundary condition, or from physical relevance viewpoint, because the shear that present at the wall, a boundary layer will start forming, which is symmetric, on both of the top and bottom faces. So we need to create a very fine mesh near to the wall. So for that you can go for bising also. So there bising is available. Bising type, you particular bising type you can select. So I'm not going to give you the tail of that. So bising factor you must calculate as per the uh, the y plus, which is non-dimensional height for your to generate the mesh by taking the reference of the first element height near to the wall, which is required as per the physics is concerned. So even though you can do calculation of the boundary layer by uh, considering the formula for laminar or turbulent flow, like 5 into characteristic length divided by under root of RE. From there, you can guess what will be the height of the boundary layer and how many number of nodes has to present. Because Navier-Stokes equation, they will be solved for each of the cell center. Now they are the cells or grid, you can call them. At their center you will be getting the value. So how many number of cells you have, that much number of equations will be generated there. And accordingly time will be taken in your problem, or you will be getting only that much numerical value as a solution for your problem. Okay. So if near to the wall a large size of the element will be taken, then interpolation or extrapolation error will be involved into it, and accordingly your problem will be sometime diverge, or it can give you the wrong numerical value, no wrong numerical solution at the end. So that has to be taken care according to the problem to problem. Okay, so I'm not going to represent you that one at present. All so just moving now to the solution. But at the meantime, I'm suggesting you your mesh must be according to the physics which is associated with the problem. Accordingly, you need to design it. Okay, so I'm considering, let's say, turbulent flow. Uh, okay, fine. And material air, I'm considering cell zone. Okay, now boundary conditions. Okay, so for this computational domain, this is the inlet boundary, this is the outlet boundary, and they are the two no slip boundaries. So at inlet, there are other boundary conditions are also available. You can select accordingly, which fit to your problem. So I'm going here with the velocity inlet. So there also it will ask me for specification method. So I'm using any random selection at present. Although this turbulent intensity generally for turbulent flow will be around 5. You can make calculation for that also depending upon the node number. So I'm taking any random value for the velocity for just to start with the problem. And then for but you uh, but you must observe that to start this problem, at the inlet I am going with the velocity. It means I am not giving any boundary condition particularly for pressure, because I already discussed with you. We can assign value only to the velocity or in terms of pressure there, because these equations, this equation for let's say for u velocity uh, contains pressure as unknown. If I solve that for pressure, then it will contain v velocity, u velocity as unknown. Okay, so this equation can only give one solution at present. So for outlet, we are going with the pressure outlet. So pressure P0 we are assigning. Okay, so it means that to start, to solve this problem also, we need to assign the boundary condition at all the boundaries, at all four boundaries. So at the inlet, we have assigned with the u velocity as 0, u velocity as 1 meter per second. So v velocity will be 0. So for pressure it will be del p by del, and n will be the normal, I'm telling you, normal to the boundary. So del p by del x will be equal to 0. And then here, del p by del y equal to 0, u and v will be 0. Similarly here also, and here we will be writing a boundary condition, p is equal to 0, del u by del x equal to 0, del v by del y equal to 0. So they are the conditions required to solve this problem. So now I'm going to the methods now. So we done today with the pressure velocity coupling method. So I'm using simple algorithm, which is similar to the semi-explicit method, as we discussed that today. And now here are the advection scheme it will be asking you. So for more momentum, see, for momentum, we have first order, second order, quick is available. CD is not available. Power law and MUSCL it is available, but we generally go with the second order. Its order, you can take them as algebraic equation where second order be the highest in a algebraic equation, then it will be representing almost second order, because as per the advection scheme is concerned, it is assigning weightage to the upstream and upstream of upstream, and its formulation, it requires some algebraic equation. Similarly, for kinetic caps, for turbulent kinetic energy, for dissipation also we are assigning second order. Okay. And then we will initialize the problem. In initialization, if I initialize it with the inlet velocity, then you will see one velocity value at in this box. But if I assign with all zones, then you will see for pressure it is assigning zero value everywhere, for x velocity zero everywhere, for y velocity zero everywhere. Okay. And I initialize it, that I already discussed with you. So it means for predictor step, you are assigning these values. They are the reference for the predictor step. And where in the method, uh, pressure standard. Okay, that is fine. Here it will be considering some under relaxation factor, that is a pressure projection approach, where pressure will be calculated. They will be the weightage to the velocities actually at the previous time level, and accordingly we will be getting some value of the pressure in the pressure projection method, and Poisson equation is generally used there. So to run the calculation, let me make it unstudy as a problem. Then you will see in an unstudy problem, time step size, that is actually your delta t. So that has to be calculated as per the stability criteria. Courant number has to be satisfied depending upon the velocity for fluid flow problems. And the total time, if you want to make a movie for a particular time, so that number of steps has to be entered, like say 100. So 100 into delta t, the total.
सतेंद्र सर, आपकी तरफ से म्यूट आ रहा है। आप माइक माइक ऑन करें सर।
शायद थोड़ा इंटरनेट का थोड़ा डिस्कनेक्शन हुआ होगा ना, तो उसकी वजह से शायद।
Maybe, sir, maybe. Okay, okay.
जी। ओके, सो आई एम जस्ट discussing this, from convergence, what residuals you are getting. So first we will see for the continuity, then for x momentum, for y momentum, then for k and epsilon. So after getting x value, means u velocity, v velocity, mass check has been performed. That is represented here in the continuity, in the residual for the continuity. So these values will be, decreasing. It means we are getting near to the, the convergence error you have set in the monitor in the residuals. So once it will be approaching that, we will be getting this measure solution is converged. Okay, so that's all from my side. Thank you for your patient listening. Thank you, Dr. Manoj, for giving the opportunity to, present some physics and some numerical ways to solve the fluid flow problems. Yeah.
Thank
So
you. Thank you very much, Satindra, sir.